In this video, we'll be talking about aleatoric composition, focusing on random composition and Markov chains. We will then talk about how to use these to create compositions in Csound using Python and the library ctcsound. First, let's define aleatoric composition. In general, aleatoric composition is a composition where some part of the composition process is left to chance and randomness. We'll talk about two methods for aleatoric composition: probability distributions and Markov chains. Compositions can use probability distributions, such as the Gaussian normal distribution in Figure 1 or the beta distribution in Figure 2, to choose notes or note durations. Compositions can also use a Markov model, which we'll talk about later. When using a probability distribution to create a composition, you first need to create some representation of notes that can be used in your composition. You might do this by creating an array, assigning numbers to notes, or by using the frequencies of each note. In Figure 3, you can see that the example in the computer music textbook assigns numbers to each note. You then choose your probability distribution and essentially make your note representation the x-axis of that distribution. In Figure 4 on the right, you can see the textbook's example using the note representation in Figure 3 and different probability distributions, including a linear distribution, Gaussian, and an exponential distribution. Now, let's talk about Markov chains. In general, Markov chains are a model of a prediction where a future event only depends on previous events. Different order Markov chains depend on different numbers of previous events. Figure 5 shows probabilities for a second order Markov chain. What does this mean exactly? Let's consider the highlighted row of the table in Figure 5. In this case, it says that if the previous two notes were G4 and then A4, then there's a 12.5% chance the next note will be D4, 62.5% chance it will be A4, and a 25% chance that it will be D5. How do we create a probability matrix like we saw in Figure 5? First, we read the input data, like the score shown in Figure 6. When reading the data, we keep track of how often a note shows up after an order combination of previous notes. After reading the entire score, we normalize the counts to create percentages. Let's go through an example of this for a second order Markov chain. We'll consider the two-note combination G4 followed by A4. If after seeing G4, A4 in the score, we saw D4 once, A4 5 times, and D5 twice, then we saw the G4, A4 combination 8 times total in the score. We then divide each of the counts for each note by this total, and fill in the probability matrix with these values. For the G4, A4 entry in the probability matrix, we put D4 as 0.125, A4 as 0.625, and D5 as 0.25. We then put zeros for everything else. We go through this process for every two-note combination in the original score. Note that we can also do this process with note durations. After we have a probability matrix, we generate a score. We first must choose a seed, or the starting value. Let's say we choose A3 then C3 for our seed. In this example, the probability matrix has a 60% chance of choosing A4 next and a 40% chance of choosing C5 next. Let's say that the computer chooses C5 next. Now, our previous two notes are C3 and then C5. We then look at this entry in the probability matrix, which has a 30% chance of choosing A4 next, a 60% chance of choosing D3, and a 10% chance of choosing C5. This process repeats until we've chosen our desired amount of notes. So how do you do this yourself for your composition? Python is a great tool for working with probability distributions, and you can combine this with Csound using the ctcsound library. To use ctcsound, you write instruments and scores using Csound syntax into Python strings. You then pass these strings as arguments to ctcsound functions. This tool will be most useful to people who already have experience programming in Python. You can see an example of this at my GitHub repository, which is linked in the description. Please direct any questions about the content of this presentation or the code in GitHub to my email at chernus@g.hmc.edu.